Hello, I'm Wade Bray, Vice President of Head Acoustics Inc. in Brighton, Michigan, and this is Take, Make, Play. This was to have been the final presentation concluding the Automotive Voice and Noise Conference that we held in May, except I made a visit to the emergency room on the day that I was supposed to present, but now I'm back as good or better than ever, I hope. So here we go. Let's start off with the devices, the take options. We can take data in electric vehicles and practically anything else as well, with a whole variety of different systems and options. There is the Scobold in the upper left-hand corner, a very small handheld 4-channel device that has also GPS capability and video capability, works with a headset or external inputs. Likewise, similarly, slightly bigger and certainly with more channels and capabilities, and also analysis possibilities, is the Squadriga 3. The HeadLab 2 is the second generation of our HeadLab modular multi-channel front-end system that can run up to hundreds, even more than that, of channels. The binaural wearable microphone BHM 3.2, the HSU 3.2 are ICP microphone versions of the artificial head and the wearable probe microphone for taking binaural data on a person or with an artificial head. We have the new HMS 5, which is the latest generation of the completely self-contained digital head system giving a digital output. The Scope is a headset interface for an iPhone, which enables you to acquire data and perform analyses on the iPhone device, listen to things back, and so on. Extremely easy for taking data on the fly as you need to. The head visor acoustic camera is very well established, very accurate, has extremely high resolution in time, and we've used it, for example, in concert hall work in order to observe the evolution of early reflections from an impulsive source on stage. I would have given my right arm while I was a room acoustics consultant, musical acoustics consultant, for that capability. The head visor flex takes the same technology of beamforming and permits it to be assembled in modular form on different sized arrays in order to get very high resolution into the low frequencies, for example. Taking sound data in e-vehicles, we have a lot of features for. We have, of course, the origin of our company, binaural equalized correct level data. Vehicle testing needs, we have availability of all multi-channel SVP, which, by the way, means sound and vibration perception. This is a term that we're using at Head Acoustics in order to replace the antiquated NVH idea, noise, vibration, and harshness, which, by the way, has been modernized by one of our colleagues in industry, suggesting noise and vibration harmony, which is a much better idea for using NVH. But let's use SVP for ourselves. Binaural sensor ready, GPS indication of where we are, and mapping. We'll see that also in some live work in Artemis Suite with data we have taken. CAN and CAN-FD. Automation, flow control. You have programs indicating exactly what is done in what sequence. The recorder task list, standardized testing module is available, and we have e-vehicle specific resolver data capabilities with very high sampling rate, specialized input channel, and extremely high number of pulses per revolution, and being able to take torque variations, etc., and observe them quite clearly. The take benefits begin with, but are certainly not limited to, having binaural in mind. We have hundreds of channels that you can do with the HeadLab system, even 1,000 or more. We have at least one customer with more than 1,000 channels on a HeadLab system. Not just for acoustics, we're now doing modal analysis, acoustic intensity, and things that people tend to think of in terms of other systems and capabilities are done, not only are done with Head Acoustics, but are done better with Head Acoustics, and more easily and straightforwardly. The interface is more straightforward. Pressure, temperature, voltage, current, tachometer, strain gauge. And we can use these things directly with Artemis Suite, prognoise, which is prognostication of noise, the planning of how something might result through transfer paths to produce a sound in an interior, for example. The sound quality analysis Scala jury evaluation tool software system, Presense, which is a simulator system including the ability to be driven in a car live, which was indicated we were able to do that actually live with a vehicle in the Automotive Noise and Voice Symposium. So let's go now to work directly with some vehicles. We're going to start off with the first generation Neo ES8 all-wheel drive, which, by the way, embodies a psychoacoustic mistake, which literally caused the car to be withdrawn from the market and replaced with a new version, the second generation, which does not make that mistake. We'll see what it is. So the 2019 Neo ES8 all-wheel drive had identical e-motors and gearbox ratios for the front and rear drive systems, both with ratio 9.6 to 1. The problem with that is that under dynamic conditions, they are not exactly the same speed, the two drive systems. They will alternate between front high versus rear, rear high versus front, and vary within those parameters. The redesign in 2020 employed different motors and ratios to keep the tonalities that would exist out of the same critical bandwidth, so there would not be modulations. There are, however, modulations when you have the same ratios. So this looks identical, but if we look at a close-up in a particular place, for example, a mark from 40 to 43 seconds, where there's a very interesting and annoying modulation issue, and likewise a mark from 52 to 58 seconds, we can observe that the rear motor in the first mark, 40 to 43 seconds, is running at a higher speed than the front motor, which is in red. And here we see, in terms of ratio, 1.0 being identity, that the offset is approximately 0.996. We have a variable ratio in the case of the upper one. Now we have switched positions where the front e-motor is running faster in general than the rear e-motor. The Ford Mustang Mach-E AWD, which is a more modern design, has different ratios significantly, front and rear, 10.0079 in the front and 9.0458 in the rear, so that over most of the operating range, there is anything produced by these two different ratios is going to be outside of the same critical bandwidth and will not intermodulate and produce modulations. We see in red the wheel rotation speed and then the front and rear tachometers. There are problems that can be unrecognized of having too slow a lookup rate for the repetition of your measurement that is in the same ballpark as the event repetition rate. And everyone is familiar with movies such as this, where, for example, you see a wheel apparently standing still, which is obviously turning because the vehicle is moving, or maybe even rotating in the opposite direction. Let's look at that again quickly. All right. So the rule is to make your measurements much more often than the rate of change of the events, and then you will not encounter this problem. Because in doing analysis results, you don't have the kind of familiarity frame of reference that you have in looking at a movie, and you would probably not, and most likely not, notice that you're not getting the information or you're getting wrong information. For example, what appears to be a regular pattern that is much too infrequent, much too coarse or broadly spaced, and not representing the reality. So now let's go and do some live work in Artemis Suite. I'm going to drop out of this and go to Artemis Suite directly. Before we return to the Neo ES8, I would like to talk about a new feature in Artemis Suite which enables you, if you have a pulse tachometer, to very easily and directly produce a ramp tachometer, meaning signal channels. You cannot analyze a pulse tachometer using the tools of Artemis Suite. Very often it's useful and important to be able to analyze the tachometer itself. If you have the ramp tachometer, you can. But if you have only a ramp tachometer, you cannot have exact phase reference. You cannot use the target order tool of the sound engineering project, which is an incredible set of tools. So let's see what we can do. Here we have an internet recording of a 1965 Jaguar XKE, a very classic vehicle, and I've had the pleasure of driving one. And if we right-click and go to Edit With, we can have a look here and go to the channel editor. In the channel editor, it's going to come up, and we can see here that we have 3 signal channels. We can look at them: left and right binaural audio, and generated RPM, which I use the RPM generator tool in order to, from the audio, generate a tachometer, which is a ramp signal. It is a conventional tachometer. If we click on it here, we can see the tachometer history, which shows that the vehicle was shifted. So what can we do to get a pulse? This is extremely easy and extremely wonderful. Simply hover over the icon for the type of the ramp channel, right-click, and do Encode Signal as Pulse Channel. Then the system wants to know, give me a geometry, for example, 1 pulse per revolution. So let's simply click that. And then it says the basic one, which you can edit. You can have more pulses per revolution if you like. Equidistant, it makes no sense to have anything other than that if you're doing something like this. So we'll keep it simple. 1 pulse per revolution, equidistant, create sensor. There it is, and all we do is OK it. And then say OK to the whole thing. Now we have a pulse channel. There it is. All we would need to do is save this result, and we have the file now with a pulse channel generated from the ramp. So let's close that mark editor without saving it. And let's go to a file that does have a pulse tachometer and do the same thing we just did. Going to Edit With, Channel Editor, and have a look. And here we have our signal channels, and there are the 2 binaural channels with no other channel as a signal channel. We do, however, have a pulse tachometer. Here we can do the converse of what we did using the ramp tachometer to make a pulse. We can right-click on the icon for the pulse tachometer, decode pulse as signal channel, and then look at the signal channels, and there it is, and it's all ready to go. It has the information it needed from the pulse channel. All we would need to do is save this new result by saving the channel editor, and we would have the file with the ramp tachometer in addition to the pre-existing pulse tachometer. That's how easy it is. Okay, let's get out of all of this and let's close that and have a look at something else. With what we just did, we need to be very careful about our choices in choosing calculation versus RPM or calculation versus time. Clearly we have a shift going on here. So we're going to take RPM versus time, specific roughness by hearing model versus time, and tonality by hearing model, specific tonality versus RPM, all 3. Calculate on the 1965 Jaguar. We can see the RPM versus time. Let's play the file. Note the RPM cursor falls back, and then the RPM range is traversed again, but not completely. Do it again. So here's a little trick. If you have the Advanced Playback toolpack in your Artemis suite, you can use the time stretching tool, which produces a synthetic noise, and you can change the playback speed. So I'm going to put that on and set 0 as the playback speed, and we'll have a frozen speed. That enables us, by grabbing the time arrow of the player, to move the cursor, and we see the dials of the tachometer. And we can see that as we progress here, we draw the entire graph, but then we fall back at the deceleration, going from 2nd gear to 3rd gear, and we begin to draw again from here. So the information that already had been drawn is now covered up by the new one. You don't know that it's there. And we go to here. So we can get a misrepresentation of what's going on unless we dice this up into segments. Let's now, instead of looking at the specific roughness by hearing model and the tonality by hearing model versus RPM, with this shift point going on, let's look at them versus time. So we'll keep the RPM versus time so we can see what's happening, but here we're going to ask for the specific roughness and the specific tonality versus time and recalculate. Then we will put these 2 up side by side, or actually alternate them. So the first time we had this, and we can see what was happening as we play. The RPM cursor reverses during the shift, runs back up but not to the original high RPM mark. So we are original up to here, and after here. When we take the time instead, we get the entire history, and it's quite different. And once again, just to show the little trick we used, we took the colored noise, which is in Advanced Playback, time stretching tool, which produces a synthetic noise based on what's going on in the time signal, and we can change the speed. We can, for example, set 0, freeze the playback in time, and then grasp the playback slider in the player and be able to increment what you hear and the cursor positions and the tachometer dials. So let's go back to versus RPM and do that. So here we have We write the entire graph up to the highest RPM, we drop back, and we start advancing again, but we advance only up to a fraction of the original RPM range. And there the original graph takes over. It's like folding a rug. What's behind the fold you don't get to see. So anyway, let's leave all of this right now. I'll close this group and close this project. Now we will go back to the Neo ES8 information and look at the front and rear e-motor tachometers. So we're going to take the RPM versus time to a data viewer and look at the rear e-motor tach and the front e-motor tach on the same file using the two different references. So by taking a data viewer with one window for everything and calculating that, we get the two tachometers for the first case, and then all we need to do is have a package which is set to take the difference. How do you do that, by the way? You can insert a new package which is marks setting channel setting and use either or both. If you do both, the operation of the marks will be taken first and then the channels afterwards. So let's take a new marks package just to show how to get a difference instead of the conventional statistics, because we have marks setting. You can take maximum, average, or minimum, or any or all of these. But if we put the properties open and we click on the name of the package, marks set, we then see that we're currently set on aggregation, which means these things. If we set difference, we can then choose the order in which we want the difference to occur. So I'm now going to get rid of that because we don't need it. And here we have a mark setting taking the first input and subtracting the second one. So we'll put it on and we will calculate again. It's this simple. And we now have that. And we can put these together side by side, hide the properties. And we can see that we have basically 13.6 to 19.8. So getting our calculator handy, we can do 19.8 minus 13.6 equals. And we have 6.2 RPM, and we see it varies a lot. And we can also see that the rear e-motor leads or is higher speed than the front one. By the way, another tip to show you is that with Control F2, we can change the type number of a window. So I'm going to make these two a type 3 window. Then I'm going to go back here and calculate the second mark, which is at the higher RPM, without the package to get the tachometer histories of that mark. Then return here, put the package on, taking the difference, put them up together side by side, and we can easily alternate between looking at this, and now we see 33 RPM total difference, and we have a big variation that covers almost the entire range in the middle of the range, and we can see that here, and it's principally the rear e-motor changing speed relative to the front, which is steadier. So if we go to the head navigator and we select Open Documents, we can have a group and control, for example, Group 2 is what we're looking at right now, and we can go to Group 3, and we can put those up side by side, or as columns. So we can alternate which one we want to look at, simply like that. So now that you know that, we're going to go to the next thing. So let me close this group, let me close this group, and let's close the project without saving. So it's ready for next time, and hide the head navigator when we get the next thing. So that was the front and rear e-motor tachometers. Let's look at this one, where we're going to take the order spectrum versus time and look at the, because again, if this were a steady RPM, we would have to do it versus time. We do have an increase in RPM, so we could have done this versus an RPM signal. But in order to observe the rate of the interferences, which we're going to be hearing and seeing, we chose time in this case. I'm taking the maximum of whichever channel had it as a representative indication of what's going on. So we'll take the first mark and the second mark at the two different RPM ranges. The gear ratio is 9.6 to 1, identically for the rear drive system and the front drive system between the motor and the road wheel. So if we put these side by side and then play, we click on the first one and let's play. We can hear a slow fluctuation with some fine detail on it. We have a faster fluctuation in the higher RPM mark. But in order to see what is really going on here in terms of the fact that there are two distinct tones of the 9.6 order relative to the two motors, which are supposedly identical, but by circumstance of the vehicle, tire pressures, dynamic load, changing the radius of the wheel, turning conditions, etc., speed of the vehicle, there are going to be differences that relate to modulations that draw the attention in negative ways. All right, this time let's use the high-resolution spectral analysis tool, which is in the Advanced Psychoacoustics Toolpack 165016 in Artemis Suite. It deconvolves the window function, like the Hanning window, from an FFT and avoids the smear. All of the information, all of the energy in the signal is represented in an infinitely thin, effectively, spectral line. So one has the effect of a perfect synchronous measurement where the period or integer multiples of a signal is exactly coincident with the block length, and no window is needed in order to avoid leakage at the ends of the block. You always have identity. So the deconvolution gives us that result, plus the fact that we can extend the block length by multiples 2, 4, 8, or 16 times. And here we chose 16 times, which by padding with zeros the empty spaces and rescaling, we get the advantage of a 16 times longer block in terms of frequency resolution, but we are getting the time resolution of the very short block. So the time bandwidth product improves in this case by a factor of 16. Let's look at the properties for a moment. So HSA versus time we're going to take at 2048 points. The initial window is important in getting the best signal-to-noise ratio, so the Blackman window is a better choice in general to give a little bit better time resolution than a Hanning window would give. So we're going to look at 2048 points to see the modulations related to how we hear them, the fast ones, and then to be able to split the signal into its parts by taking a longer FFT size, again multiplying by 16. We're going to take 4 iterations so that we see the maximum sinusoidal fragment, maximum magnitude, and anything less in increments, the next one, the next one, the next one, down to 4 times. So we're going to suppress the background spectrum, the FFT spectrum, so we see only the result from the HSA. So calculating that to a mark analyzer with a column per window, I should say a column per analysis, instead of the single window we were using before, and calculating both of these, I took the liberty of calculating them already. We're going to see this. Excuse me. So here is our dominant order effectively interacting and producing rapid frequency modulations, plus some slower variations. However, if we look with more frequency resolution, we see the 2 different tones. These are both 9.6 orders, one of the front drive and one of the rear drive. So their spacing in frequency is very small. We can expand this scale and we can label in order to demonstrate that point. So for example, taking the middle of this event and using a label cursor, Shift L, we will label that, and we will label this. And they are 266.02 dB, 980.1 hertz, and 956. So basically 56, call it 60, 20 hertz. So we have an approximately 20-21 hertz modulation rate going on in between these two. And that is certainly audible. All right, let's go to the next example. I believe we're still on the Neo, so we will close this without saving, and we will go to the 02B. Did I do this one yet? Yes, I did. This was the dominant order interference. That was number 2AB, so we'll go to number 2B now. And here we have FFT versus time, specific loudness versus time by the Moore-Glasberg method in order to give more spectral information, more spectral detail than the Zwicker does, which we can use in this case, although it isn't quite as accurate in time, particularly in low frequencies, as the Zwicker method. modulation spectrum versus critical bands, and weighted modulation, which is modulation spectrum versus critical bands, but weighted by the specific loudness of the signal. So if you have a very low loudness or threshold of hearing signal, even if it's strongly modulated, it will have essentially no effect on the perception, so the weighting will give a very, very low or even no number. If, on the other hand, it's a loud signal and is moderately modulated, you will get a very high result magnitude in a weighted modulation. So this is psychoacoustic representation of perceived modulation. This is the direct measurement of the modulation. So let's have a look at these on the earlier and later marks where the 9.6 orders of the two motors are presenting their interesting festival of modulations. So calculating, here we come. So here is the FFT versus time. There's the 9.6 order. Here is the loudness of it. It is by far the dominant loudness. That's a major point in itself. Here is the modulation, and we can see that there is a slow dominant modulation, but then there are faster ones. The weighted modulation tells us that really only the slow modulation is important in the perception. So we can, for example, let's make this full screen, which I can't do because it's all in the same window, but we will use the label cursor and label this, and that is about a 2.7 hertz modulation, which is as we hear it. This is more the 21 hertz modulation that we described moments ago. Okay, that was 02B. Let's proceed to the next thing without saving that. And go to the binaural multi-measurements. You can tell already that I'm a proponent of taking multiple measurements because perception integrates many different things. How tonal is it? How modulated or how rough is it, which may be at different frequencies than the tonality, may be at different frequencies than the peak loudness, but they all contribute to the overall perception. So if you don't measure enough things with a complex, particularly technical sound, then the information is not present to enable you to solve the problem, design the sound, improve the situation. So let's look here at tonality, frequency versus time. What is the frequency of the tonality, which is done in the case of the hearing model tonality by taking the spectrum of the autocorrelation function, which is what determines the frequency of the tonality. It is very accurate and has a very good time response. The tonality magnitude versus time, and then the order loudness versus time. So let's start off with the maximum that occurs for either ear, and then we will turn the package off and look at the value of the two channels themselves. So let's orient ourselves with the lower and upper cases. So here we have, for example, with the label cursor, the frequency of the tonality, 726.6 hertz at this point in the history. The black curve is the 9.6 order loudness, which obviously fluctuates. And why I'm not hearing that right now, I can't tell you. But let's play this one. So the red is the magnitude of the tonality, the green is the frequency of the tonality, and the black is the loudness of that order. So we can see that we have variations. All right, now let's close those. Let's turn off the package and look at the left and right contributions, because for things like tonality, loudness events that stick out above other things, and modulations, if you have a difference between the two ears, it becomes significant and draws the attention more, usually in a negative manner. So now let's look at these same measurements where we see the left and the right. So this is going to be a little bit busier graph, but it's more informative. So the tonality is the green and the red. Left ear green, right ear red. So the tonality frequency. The tonality frequency is essentially the same. Okay, the black and the blue are the tonality magnitudes. So the black is the left ear, has a higher tonality magnitude with less variation than the right ear, which has a lower magnitude of tonality but with more variation. Likewise, the order loudness is in hot pink for the left ear, which is this trace, and also, but slightly differently, deviant and modulated, the right ear in the tan yellow color. For the other channel, or the other mark, we have again deviations, and let's play that. So the modulations and the tonalities are more noticeable when we deviate between the ears than when we have a very similar level between the ears. So that's project number 3. Let me keep my wits about me here, and we'll go to project number 4. So I don't want to save. We'll go back here, and we'll find from our list the Bolt Hill Acceleration. This is a Chevrolet Bolt electric vehicle. We're going to take the FFT versus RPM and the specific tonality versus RPM. By the way, we used through the kindness of the Kistler company, we used a Kistler wheel sensor with 1,000 pulses per revolution in order to obtain data on this vehicle. And that was extremely informative. So we'd like to thank Kistler very much for that. I would like now to, first of all, in the view menu, turn on the video, because we took video through the windshield, and we also took the GPS signal. So with the GPS signal, we can automatically link. We don't have to do anything about this. It automatically produces a map in the map viewer. So as soon as I begin to play something, so we'll calculate these two things. We will then get the video in the lower screen and the map in the upper screen, and they will animate as we play. This can be done with any of our front ends, and particularly usefully with the Squadriga 3 and the Scobold, with their GPS sensors directly connected. So here I'm simply going to zoom. This is the Kensington Road Hill above Grand River, above our office, actually above Buno Road before it goes up the steep part of the hill. So Kensington Road, Head Acoustics Inc. are down here, and we are climbing the hill because this was our closest nice hill. So here comes the video. This computer is rather busy making a Camtasia video, so there may be some hiccups in the playback of the video. Otherwise, the video plays very smoothly. So let's proceed here and play.
Climb from standing start. Start.
I have to tell it where we really are here, which is that file. And that file. So we'll start with this one. And we can see the car is beginning to climb the hill here in the map. And a car will come down the hill and pass us, and we'll hear that in a moment. Get some tonalities. Notice these tonalities, which are, if we use the data cursor, at a frequency of about 2600, 2800, 3600 hertz. Some research at General Motors, which was published about 2.5 years ago now in the SAE Noise and Vibration Conference by Glenn Piatilla and colleagues, indicated that the annoyance of a tonality is a factor that is more pronounced with higher frequency tonalities and is not directly related to the noticeability of the tonality as a tonality, which is very well modeled already by the hearing model tonality. So General Motors worked on this, and we at Head Acoustics also worked on it, and we came up with a weighting, and I would like to show you that. Now that we've seen the map viewer and the videos, this exists and is available on all the files we made on that vehicle, so I can simply close them because we don't need to show that to discuss the properties. I'll open and save the properties in view, and we're going to have a look at the tonality measurement. There's a switch for tonality annoyance weighting, and we see that we have a unity weighting up to 1 kilohertz. Then the weighting gives a higher and higher magnitude as the frequency of the tonality increases. So tonalities above 1 kilohertz get a higher magnitude. So we can see here, for example, and by the way, the left graph is according to the wheel RPM, and the right graph is according to the e-motor RPM. The e-motor ratio on this vehicle is 7.05 to 1. So we were able, from the wheel Kistler 1000 pulse per revolution sensor, to multiply by 7.05 and derive the E-motor. This is not exactly the same as measuring the E-motor because that will show differences in the drivetrain between the motor itself and the road wheel. And those might be a factor. In this case, they weren't in particular, but we can always generate a tachometer by knowing the ratio in either direction. So at any rate, let me calculate these again, only for one of the files. I think I'll do the first one, so that we have the wheel RPM, and we will take it again. That's this one, with the tonal annoyance on. Now let me turn the tonal annoyance off and recalculate, and you'll notice the difference. Hide the properties. Waiting for the calculation. We have here the straight tonality hearing model, specific tonality result, versus the one with the tonal annoyance waiting on. Incidentally, at this particular time, the frequency of tonality does not have the switch for tonal annoyance. We have been noticing that in some cases, like this one, there may be some tonalities at a little bit lower frequency that are at or under 1,000 hertz, which actually are a higher magnitude with the tonal annoyance waiting off, and thereby show up as the tonality frequency, whereas the perceptual annoyant frequency tonalities, which are represented with the tonality waiting on, don't get shown in their frequency. So that switch is being added in a forthcoming version very soon of Artemis Suite to be able to represent those frequencies according to the tonality weighting. So there you have it, with and without tonal annoyance weighting. That is extremely important with e-vehicle sounds and higher frequency sounds. So that was 04. Now let's go to the next project, which of course is 05. And here is multiple two-dimensional measurements, loudness versus RPM, and tonality magnitude versus RPM with just one of the files. And we're putting everything in one window, which in a 2D analysis result can be very useful because you see the relationships. So the tonality magnitude with the annoyance weighting on is the red curve. The loudness is the green curve. So we can see and play.
Climb from standing start.
Which I actually would like to tell it that we're doing the same thing that's shown in the mark. Here we come. That was the voice of my colleague Steve Porter, who took those data. We saw earlier the Neo ES8 first generation, which made a psychoacoustic mistake of having the all-wheel drive mechanisms have the same ratio at front and rear, which caused problems of the relationship, which is not identity, but is close enough to it to cause modulations that vary considerably in their rate and their magnitude, and is an annoyance factor. So that car was actually withdrawn from the market, and different ratios significantly so that that would not occur, brought out. So the current generation of the Neo ES8 does not do that problem that the first one did. So the Mustang Mach-E is another very good example of having separate ratios, 10.0079 for the rear and 9.0458 for the front. So I was able to find the seat track z-axis was a very good place with the accelerometer signal in order to identify orders that show very clearly the two different tachometers. So we'll calculate that. We can see them here and we can listen. Which is actually this file. And once again, we can draw a box and make a measurement with the label cursor. Shift L, so we can, for example, label that frequency and this frequency and see that one is 3,357 and the other is 3,053. So they're basically 300 hertz apart, which is well outside of a critical band. So even though at a very low RPM, no matter what the different ratios are, there will be a span of time, or RPM, in which there will be intra-critical bandwidth possible modulations. The thing to do at that point in your history is to try to either eliminate or reduce all tonalities or have one significantly different from the other so that there is only one tonality present and any modulation interaction will be very weak. So all the rest of the RPM, by far most of the range of RPM of operating the vehicle, has these tonalities or these tonal components well outside of individual critical bandwidth, so they will not intermodulate in that manner. This is a very good thing. Okay, let's go ahead now with the 07 project about the Mach-E. So the 07 project is a very interesting one. Very often in teaching about order analysis and powertrain issues, I get the question, when is it better to do an order calculation by means of, and let's show the properties, the method of adapting the DFT size, and the method of, actually we're getting ahead of the game right now, so we're going to do the modulation spectrum, the FFT, the modulation, the specific tonality, and that's the next project is going to get into those, so I'm getting ahead of myself. Please forgive me. So we'll start with the whine sweeps again, as we've been hearing them, and take the modulation spectrum versus critical bands, the specific tonality, the FFT versus RPM, and calculate all of that. So we can play. Here comes the 117.75th order, which is the topic of the next project. Note that modulation. This is a resonance, which is significant as a tonal factor, and also, interestingly, as a modulation factor in the earlier part of its history. Here's the modulation spectrum versus critical bands. 50 hertz to 7,000 hertz in all cases, signal frequency vertical, and rate of modulation up to 40 hertz on the horizontal scale, and the magnitude of the modulation up to 20%. And then in the color maps here, we have the hearing model tonality magnitudes. We don't have significant high-frequency tonality, but we do have this one. So let's play this again. We'll actually use a playback spot to begin with. Right-click, playback spot, the box you listen in, and center it here. So you can hear that. And you can also hear the modulation. I mean the resonance. Ooh. Like that. So let's now go back to a conventional view and expand that to full screen. Oh, before I do that, I want to show you a little tip. If you use the conventional filter cursor in a mark analyzer, and here we have multiple analyses, you get an advantage that the filter cursor indicators show up in all of the graphs that are spectra. And this is very useful because you can see any relationship. So let's get the filter cursor mode, which also, of course, opens the playback filters. So if we grab a cursor, you can see it shows up in all the graphs. So we can place it here, for example, and double-click, turn the filter on. And I had pre-adjusted the magnitude by rolling the mouse and the bandwidth by holding down Control and rolling the mouse, so that basically this filter is canceling that resonance. So let's listen now and then turn on the filter partway through and off again and so on. And I'll do that by the button. Listen for ooh. That is likely to be the tire resonance, although tire resonances are usually in the mid to high 200 Hz range. So that's not a terribly annoying resonance, but it is noticeable as a tonality, and it does show up weakly in the tonality metric. All right, let's close the playback filters. Let's get back to a normal cursor and then move to the next thing. By the way, if we zoom on this region, we can see that there are stripes. And with the modulation analysis, we find that we have modulation at that rate. And if we use our label cursor and label it, we find that it's 5.127 Hertz. If we multiply that by 60, we get the number of events per minute, and we can see if it's related to the wheel RPM. So the wheel RPM here is approximately, let's get the data cursor, Shift D, 321 RPM. So let's get our calculator and multiply 5.127 by 60. So 5.127, 5.127 times 60 equals 307.6. So this is definitely a once per wheel revolution event, and it clearly shows up as stripes like this. If we use a cut function, we can see them also. So with that in mind, let's look further. And now we'll go to the 08 project. I don't need to calculate, I mean to stop it, and close this. So the 08 project involves tonality and loudness of the sweeps. And we're going to do a calculation through a bandpass filter and without the bandpass filter. So what am I doing here? Okay, the whine sweeps first bypass and second the bandpass filter. Let me see what the properties of it are. 117.75th order, flat top Chebyshev, 6th order filter. It's quite steep and it tracks the 117th order of the wheel RPM. So this comes and goes, and we're going to see that in the next project. And for some reason the filter is not actually working here. So why not? Two D metrics. I don't have any 3D metrics active. Why am I getting 3D metrics? So there, that's what I expected. Okay. So there we have. Now I know what's going on. I'll go back and do it again. I had confused the computer for some reason. No filtering and filtering. So when you have filtering, you can put bypass in the filter pool as well and get a result without the filters. So that's what we're going to do. And we're going to look at the whole signal and then the signal only in the order tracking band centered on the 117.75th order. So this is the whole thing. I think I have too much going on in my computer for its memory right now. So there we see the loudness in red, and we clearly see the once per revolution issue, and then it tends to disappear more in the latter part. Very strong here versus the overall signal with the resonance at 300 Hertz, as we noticed before. Okay. If we turn off the package that takes the maximum of the channels and look at the binaural data and recalculate these tonality and loudness results in the single window, there is the overall. And notice where there is difference between the right and left ears in the loudness, which are the blue and the black curves. We notice more the tonality and the variation. that's 0.8. Coming up 0.9. I began to mention ahead of time, and shouldn't have, the question about which method should I use, quote unquote, about calculating orders. There is a method called variable DFT size, where the sampling rate is maintained constant, but the Fourier block size is adapted such that all orders are synchronous to the block length. Block length is adjusted. And the other method I've listed here is RPM synchronous resampling, where the block size is kept the same and the adaptation is made by resampling the signal such that according to the sampling rate at any moment, which is RPM linked with the tachometer, you have the integer relationship of the block length to the order period. They give different results, but you usually don't know that unless you go to an extremely high resolution in time, or RPM. So we're taking order spectrum versus RPM. Notice, please, that we are taking step size in RPM as 0.1 for both methods, the variable DFT and the spectrum versus RPM. The results are going to be quite different, but yet they contain the same information. So let's have a look at what this means, hiding the properties and calculating. The resolution is the same in the two order spectra. We're looking, for example, I should put this up at 1/4 order resolution in each case. It takes more calculation time to do this many iterations. But we can see that at lower frequencies, we have a lot of information going on, and we can see a difference. We have a lot of frequency detail. This is frequency sensitive, the variable DFT size method. And the adapting the sampling rate method is more order sensitive. So if, for example, I can move these labels out of the way, we do a zoom, we can see that we have lines of discrete frequency and we have orders. And we can see here, for example, if we use the data cursor, that we have the 117.75th order. We also have, toward the right edge, 116.75, 115.75, 114.75, and then we begin to lose detail. But we see at least those three, and they are separated by one integer order number. They all are something 0.75, but they're separated by one order number, with the dominant energy being in the 1/17th 0.75. If we look over here, we see more orders. If we take a narrow bandwidth, for example, half an order bandwidth, and look at this, we will see the time resolution. And if we look at this, we will see the orders standing still. So let's do that. Let's look at a cut. In this case, I'm actually going to recalculate it so that you can see it better using a shorter portion and an analysis which is already zoomed in. So order spectrum by variable DFT and by RPM synchronous averaging over a mark between 200 and 600 RPM. So we're looking close up at that region. I'll also rescale the magnitudes slightly, which I already did, so that we're looking at 30 to 48 dB sound pressure level. So there we are. Let's do a cut. So if we come along here and put the cursor on the 117.75, as close as we can get to it, we can see the cut of the level versus time, which is along that line of that order, in the upper left window, and we can see the spectrum at that time in the upper right. But watch what happens when we play in the upper right-hand window and how very different that is when we play the other result. So I'm going to play. All of the spectral lines move from right to left because we have increasing RPM. And as they pass a fixed frequency point, you get exact time reference of this rate of modulation, which, as we've seen already, is wheel related. Let's go through that one more time, and we'll stop before we get to the end of it. You'll start to see it picking up here, centered on the 117th order, 0.75. All right, let's stop that. Let's get out of the cuts mode. Let's now look at it over here and do the same thing. Put the cursor on 117.75 and play. And look what happens. We have stable on the order scale positions. Nothing moves except vertically, which is the magnitude of those orders. If we take a level versus time or level versus RPM bandpass encompassing several orders, we get exactly the same result in the range of frequencies or times where the modulation is occurring. If you were to take, for example, one RPM step or even a half RPM step, you would get practically no information or no information at all about this resolution. So it really is, very interestingly, and it can be proven with the high-resolution spectral analysis, that the variable DFT size is showing real information, that those lines which are sloping, they're not vertical, of constant frequency, actually produce a slight frequency modulation, which will show up in the HSA result of an order which is modulated. And so that, in effect, validates that aspect of the variable DFT size method. Okay. Did I do here, and do I have in another project? No, I don't. So let me see if I can get back here and do it without further ado. A 2D measurement. I can't get there quickly enough in this particular case, so I won't show you. But if you do a cut, you will see the same result from a certain frequency upward, but the frequency resolution when you do RPM synchronous resampling will be very poor in the lower frequencies and good in the upper frequencies. But in the case of the variable DFT size method, you have very high resolution frequency at all frequencies. So we saw what that means, all right? Keep that in mind, and please consider to use extremely small steps in RPM, no matter what method you use, and you'll be able to see the information that is provided that way, 0.1 step. If you get down to even 0.3, 0.2, you see this. You don't see it at one step RPM resolution. Okay. Nearly at the end of our presentation now, we will come to offset orders. I just want to be sure. Yes, okay. So here is a very old case where we have an FFT versus RPM of an industrial drive, an electrically driven industrial drive. And we see, obviously, orders. This is an accelerometer signal. We see there is an obvious order which is rising. The RPM is rising of the mechanism. We also see an order which is falling, and which is obviously an order. And we see here are orders which are parallel to, but never the twain shall meet, and these are the so-called real orders, and the stronger order happens to be not able to be found with the data cursor. So if we have the data cursor here, we find, for example, that we cannot align on this order. So what's going on? We can align on this one. So this is the 68th order. If we come back down to the origin, and we could use a zoom in order to help us out, or we could simply place a marker like here, double click, and put the little round dot, and then climb directly above and find out what our offset is. It appears to be about 100 Hertz if we look at the left-hand side. So if we come back here to our data cursor, get a new one. I'm going to go back to the zoom cursor to break that setting, and then go back to the data cursor. We can ask for, right-clicking, this field, and see what it offers. And it offers offset. So if we turn the mode on and enter a number and hit enter and then click outside, now we have an offset order cursor which will align on the orders that are parallel to and offset by 100 Hertz from the actual. So there is a shortcut for this by Control F2. So if we do a Control F2, we can simply turn the offset off, and we are back to a normal RPM cursor that aligns on actual orders. If we put the Control F2 back and turn the offset back on, then we have our offset orders. So these I call parallel offset orders because they are parallel to and do not cross the other orders. There is also the so-called mirror offset, which occurs typically from inverter drives for electric vehicles, where you have the running frequency of the inverter. And we're going to see that now by switching to this one and calculating and expanding the high frequency scale so that we can get up here where the event really is. So let's maybe go from like 0 to 20,000 or 18,000 RPM. And there we have two families. We have the inverter running frequency is 8 kilohertz, and the second harmonic, we actually have a stronger family of these so-called crow's feet patterns, which center on the inverter running frequency. So if we take a shot that this is an 8 kilohertz offset, then we will find that we have an order cursor, and we can also perform analyses and so on based on offset orders, not just conventional orders. So let's go in here, get the data cursor, which is that. Then right-click, turn on the offset, and enter 8,000. And now we have the ability to read positive and negative, which are above and below the horizontal line of the inverter running frequency of 8 kilohertz. And we were pretty good on nailing that. You can iterate and try it out just by changing the numbers. And if you are correct, your offset orders will appear in an order analysis as horizontal lines everywhere. If you are too high or too low, they will have a curve upward to the left or downward to the left of the graph. So it's a quick way of being able to test yourself. So for example, if we go here and turn the offset off, then we're back to a conventional RPM cursor. So with that in mind, let's consider a very clever and interesting thing, the synthetic order sound that can be operated in the Mach-E Mustang. They call it the propulsion sound. So here we have the propulsion sound.
Okay, we're going to do another what?
All right, that I want to calculate so that we get the mark. And that's the voice of my colleague Shane Seed, who took these data. So here we go. It is not an electric vehicle sound. It is also not really quite an IC sound, but it suggests an IC sound, and it's very interesting what's going on here. If we expand this, this is relative to the road wheel tachometer, and we get a data cursor, Shift D. The curving line is order related, is tachometer related, because this is an FFT versus time. It's not an order spectrum. So we find that we don't align on anything with the actual RPM until we get up here to, for example, 117.5, the 56.6 orders and so on, which are actual orders relative to the e-motor and the road wheel. So what can we do? We can do the offset. So I found by a little experimentation, let me just rescale this a bit, that if I do an offset of 30 hertz, some of these synthetic orders align very nicely on 30 hertz, like that one. That is a 2.25th order aligned on 30 hertz, and this is a 1.5th order aligned on 30 hertz. Okay, nothing else aligns. See, they start to deviate. So let's try a different offset. Let's now go to a 70 hertz offset. And we find that at a 70 hertz offset, there is a prominent fourth order, which suggests, of course, the V8 engine firing rate. So that is really the only thing that aligns on an offset of 70 hertz. We have others that align on an offset of 100 hertz, so let's do that. So in assessing somebody else's trickery or developing your own sounds, there we go. See, there's a 100 hertz offset, which is on 5.5 essentially and 6.5 orders relative to 100 hertz offset. So this family, which interrelates interestingly, is enough to give you a suggestion of an IC-like power, and also to tell your brain, hey, this is really more fun to drive now. than simply hearing the normal sounds of the mechanism. It's a mind game, and a mind game can be extremely robust. So I direct your attention to the McGurk effect, and to consider the fact that, like this, you can produce sounds in the interior of the vehicle, and electric vehicles form a wonderful opportunity, as we are evolving and blooming into this age, to develop sounds and produce synthesis of order-related sounds and other things in the vehicle interior, to produce moods, to be situation dependent, to make the vehicle more fun to drive, to get a sense of a better handling vehicle, or one you're more excited to drive on the twisty roads at a given price point where it can't be entirely designed in mechanically, but yet not be out of character when your brain is using this other sensation in order to underlie something. So bear in mind, you have 86 billion neurons in your head, and you have multiple senses, and your multiple senses do things like integrate this sound in order to make that vehicle more fun. And here's how they did it. This is very clever, and I'd like to give kudos. I talked with them if it was okay to mention this, and it is okay to mention it. So hereby consider it mentioned. All right. From there, we leave the Mach-E, I think, and we go to our last items, which is the use of advanced psychoacoustic metrics and conventional ones in ways you might not consider orthodox in terms of structural measurements. This is a metal plate which is being tested for its modal behavior with and without a damping material. We have the bare plate being driven by a shaker with a stinger from the center point and suspended on soft ligaments, and it sounds like this when it's bare. And it sounds like this when the damping material is on. Bare, treated. Okay, we're going to take A-weighted level versus time of this broadband white noise excitation, and loudness versus time by ISO 532-1 Zwicker loudness, which takes into account the temporal masking of loudness and growth of loudness of the human hearing mechanism. So we'll calculate these 2D measurements to a single window. We'll put those windows up side by side with the bare plate on the left. We see the loudness history in red and the level history in green. The level is 72.05 dB SPL, 68.05 dB SPL in the damped case, and the loudness went down 19.6 as opposed to 23.6. That's noticeable. The loudness changed more and also is less irregular in the damped case. Bare, damped. But let's unleash some other metrics. So let's close this. And now let's put on column per analysis window and do some 3D metrics. Let's do the FFT versus time, the specific roughness hearing model by ECMA 418-2 2020, and the specific tonality hearing model versus time, and see what happens. So we are going to get the two graphs, and we'll alternately look and play the two sets of graphs. So here we have the FFT versus time, and we see that the roughness is erratic, but is concentrated in frequency at around a little above 700 hertz. We also see that there is effectively a double set of tonalities which are varying and attend not when it's strong in one, it's not in the other, and when vice versa. So we can see here versus the damped case, the roughness goes away, it's concentrated, and the perception with it. We essentially only have one tonality left instead of two, and higher magnitude. But please note something else. We can, of course, take 2D metrics, like you can take loudness versus time, which is the summation of the loudness at all the different frequencies in the different critical bandwidths over time. So we're going to get an interesting, perhaps non-helpful result if we simply take roughness versus time by hearing model, because we can see here we have condensed roughness that's important, that this graph shows us, and that we're hearing. But the random ground clutter, like in the weather radar, is relatively low, whereas when we damp, we have taken out this hot region of frequencies, which was rough, but the ground clutter has come up over an average a little bit more. So unfortunately, if we simply take a 2D measurement here, let's close this group, and let's now do our 2D measurement back to one window. Tonality, magnitude, let's do tonality, frequency, Yes, actually, and roughness magnitude. So we'll again take the maximum of the two channels of this binaural data set, pair of data sets. So we're simply taking the 2D, and the roughness result is not going to change as much as we think it should from our perception, but there's a way around that, and that is to take a cut at the frequency where the concentration occurred. So here is the Bray case. The green is the tonality magnitude, the black is the roughness magnitude, and the red is the frequency of tonality, which clearly is oscillating between two very stable discrete frequencies of the tonality, i.e. modal behavior. When we damp, we only get the upper frequency remaining, and we get still a lot of variation but similar overall magnitude of the hearing model roughness. This is the contribution of summing over the ground clutter. If we want to get this really right, we need to consider back with our 3D measurement that the roughness was around 770 hertz, more strong than anywhere else. So if we take the roughness cut at 777 hertz instead of the total 2D roughness and then make the measurement, then we get the result that we would expect, and we get a very strong, very clear differentiation of these signals. So here we have again, green is magnitude of tonality, black is magnitude of roughness, and the frequencies of the tonalities in red. Now the tonality magnitude and the roughness magnitude go way down, and we have only essentially one frequency. So this very strongly quantifies the bare versus the damped case. So I submit that using advanced psychoacoustic metrics can be extremely productive in ways that they might not normally be thought of as being used in. Likewise, this could be an opening to consider where is this metal plate going to live. Maybe it's part of something that is responding to transients like door closures or some vibratory information, such that these effects and these metrics are directly valid as opposed to being used because they work. But being used because they work is good enough. This works extremely robustly all the time for this kind of metric. And this customer was very surprised, and I believe has been doing this ever since. So there we have that. Let's close it and do our very last thing, which is kind of fun. So closing. We talked briefly about using the RPM generator to look at an FFT versus time where we know what a clearly defined order is and say, okay, that is the whatever order. Let's have a look at a project where we have a frequency modulated and amplitude modulated situation. Measuring frequency modulation via the RPM generator is the title of this. So we're going to start. This is the original recording of a mechanism driven by a small electric motor. So we're going to start here with the conventional spectrum versus time, and we'll look at modulation spectrum versus critical band with a small block size because there is a buzzy fast modulation, but there is also a slow modulation. And those need to be looked at with different block sizes and different scales of the horizontal or rate of modulation axis. This will become self-evident as we see these results. So here we have the FFT versus time, and here's the sound. Let me put the playback back to normal. Maybe a little more level for you on the playback. So we hear this zzz, bzz, 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 which, by the way, can be evaluated in terms of what's going on by changing the playback speed. So we hear there's a wow, 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 wow going on, both in amplitude and frequency, as well as the more continuous buzziness. So using a block size in the modulation spectrum versus critical bands of 1024, we get the buzz modulation, and in looking for the slow modulation, we have to go to 65,000. So coming back to our results from those two settings, we have a scale of up to 200 hertz rate of modulation, and we see the buzz at label cursor. We're going to label it, and the strongest is right about there, at 42% at a rate of 85 hertz approximately. But this is the slow modulation using the big block size and restricting the scale to 10 hertz. So all this other stuff is going to be way off the right-hand side of the screen, beyond the screen. And we can look here, for example, and say all of this stuff we can measure, and we can use our label cursor again. And this is 2.014 hertz rate of modulation. So let's now look at our FFT full screen. We have to have our normal cursor to do that. Come on. Shift, not Control. All right, now make it full screen. We'll simply take again the FFT versus time by itself. And we can zoom this. Or we could scale by typing the numbers on the left side. And see that, for example, we have some candidates, this one in particular, for observing the frequency modulation at a rate, at a signal of frequency at about 25 something hertz. So why don't we use the RPM generator in order to put a tachometer on that? So that's what we're going to do next. So we just did the first step. Now it says what to do next. So using that to help guide myself and you, it says with the tachometer, we can measure versus time. So let us now get from this signal, right-click, Edit with RPM generator. And we need the properties in order to make some choices. So here, we are going to zoom so that we're looking at that nice, clear amplitude and frequency modulated tonal component at about 25 something hertz, 2500 hertz. So looking like this and scaling so we can see it better. We are going to say mark the prominent order. Here is where the fun starts, because we're going to tell it we don't know what the actual RPM is, but what we want is to have the frequency be read out by the tachometer, exactly the same as the frequency we see here in the frequency spectrum. So this is a hertz scale. If we take a 60th order, 6-0, any 60th order has its RPM and hertz identical. So we're going to say mark the prominent order, click on here. Having chosen our block size, which happened to hit right on the nail already, we can change the FFT block size in order to tune in for the best result for this to look for things. So there, we're going to tell it this is the 60th order. We're now going to select the most frequent lookup, the highest amount of detail, and then simply zoom back out in order to restrict the reference zone, because we don't need the computer to take all this other stuff into consideration. It just wastes time because that is so strong, that component. We're going to do this, and then we're going to zoom back. We don't really need to zoom back for the calculation, but just to show you what's going on and maybe to further help ourselves a little bit and save calculation time. Now let's select Start Detection. And it's working. And there is the RPM. And let's scale this back up so we can see it nicely, and we see the hertz numbers and so on. And we see the result. Our calculated tachometer is overlying very nicely this spectral line. So there's the tachometer, and we should see that same detail on an RPM scale, but it happens the numbers are exactly the same as the hertz scale because we chose the 60th order. So there is our 60th order. We're very good. That is an incredibly detailed tachometer, and it happens to have exact phase relationship with the signal. There is no propagation delay to a microphone or anything like that because we took it from the signal already present and told the result to be calculated. So we can now save that result, which is this, but I already saved it. So we're going to simply go there now in our project, having done our work with the RPM generator, and now say, okay, we have generated RPM. We are going to tell the properties to use the generated RPM signal to measure this 60th order and see if we get a flat spectral line. So if we now calculate the signal, the microphone signal, with an order calculation, order spectrum versus time, and RPM versus time to show as well, and we can calculate that. And if we get a straight line, which we essentially do, we are proven, and there's our tachometer. to have a good tachometer. So now we're okay. The next thing we need to do in order to do our frequency modulation measurement is to measure not the signal but the tachometer. So put the check mark on our ramp tachometer, which was generated by the generated RPM, the RPM generator. This is a signal channel. It is not a pulse channel. Because it is a signal channel, it can be analyzed by the analytic tools. So at this point, it says use only the generated RPM channel and analyze it, measure the tachometer. So take the average rate by spectrum versus FFT average using a very big block size, and then choose the rate by FFT versus time. And let's look at those. So if we now ask for this generated RPM and we make these two calculations, let me hide the properties. We see here the rate of the modulation. Maybe I can expand the number here. So if we use the label cursor, Shift L, we can see that the rate of modulation is 2.151 Hertz on the average and harmonics. And the vertical scale, which is labeled in RPM, is actually the Hertz deviation of the frequency modulation. And if we go over here, this is an FFT versus time. This is the best result we can get using a Blackman window and a very high overlap using FFT versus time. We can get very, very much better by using HSA, high resolution spectral analysis versus time. But we'll see that next. Anyway, let's get a cut of this. So we're going to go to the cuts mode, and we're going to observe, for example, putting along here the 2 Hertz line. We can see that is the trend of the rate of modulation. Between maybe close to 7 Hertz rate and down to about 5 Hertz rate. And as we move along or play the signal, which we can do by hitting F12, we can see as we enter the calculated part what is going on here. Now, we're playing the tachometer. This is why you're hearing clicks. We're playing a DC signal on which is riding an AC term. The dominant level is DC, so don't play this on anything, especially not anything that gets the DC pass through and can damage your headphones or your loudspeakers. So I want now to leave the cut mode and do the last thing. We're still looking at the tachometer signal. We are now going to take the high resolution spectral analysis. 1024, 99.6% overlap, Blackman window. Let's look at this. So 1024 points, Blackman window, resolution enhancement 16, 2 iterations. This is an important point. We just mentioned that we have a DC signal with an AC term riding on it. Ordinarily, you would expect if you have only one tonal component, or you want to look only at the strongest tonal component, if there's more than one, that you would use 1 iteration. If you use 1 iteration, in this case, you get no result. You scratch your long white beard if you're Gandalf, and you think, well, why is that? And then suddenly it dawns upon you that the major term is the presence or absence of the DC signal, and therefore you won't get anything. So if you make 2 iterations, then you can see the second one, which is the AC term, and you get the calculation of the first one, but it is so far down in frequency that it's not an issue. So we're going to take 2 or more iterations. 2 are enough, and then we're going to calculate this. So here we go. Hide the properties. And there, we're going to take the cut. So if we now play the signal, the upper right is going to be the magnitude and the frequency of the rate of the modulation, the deviation of the modulation. So again, horizontal is the rate of the modulation, basically around 2 Hertz. The vertical is the deviation in frequency of the frequency modulation. So this is a dynamic, high-resolution amplitude and frequency modulation metric tool that was done by faking a tachometer off of a tonality and telling it was the 60th order and using high-resolution spectral analysis. So several tricks were pulled out of the hat by Gandalf at this point. Here we go. Let's play that. Get the cursor in here and animate. Again, we're playing the DC signal. So the clicks are immaterial. There is our frequency modulation deviation vertical and our rate of the modulation horizontal. So Head Acoustics is working on a direct metric for frequency modulation, but in the meantime, this works extremely, extremely well. And with the result from a generated RPM, you have a time signal channel, which you can analyze using tools like HSA. So I rest the case. And look here that we don't have anything else for all of the things we've discussed. We've hit everything, hopefully in a helpful way to you. So thank you very much for allowing me the honor of providing this presentation. And I'm, again, very sorry that for those of you who were in attendance on May the 31st, that I wound up being knocked quite out and almost more than that, unfortunately. But I'm back, and I think I'm better than ever, and I look forward to working with you again. Please, please contact me, and I'd be glad to help. Thank you again.